Hello, hi. So yeah, first I want to say it's an honor to speak on that stage. We've had plenty of really interesting talks. So yeah, I must say the bar has been set pretty high, and so hopefully that talk we're going to have right now on code injection is going to be as interesting as the talks I've enjoyed yesterday and today specifically. So it turns out it's quite hard to find names for presentation. I found myself scratching my head, trying to find one sentence. It was quite hard. So you see there is module loading, there is injection. So essentially that's a stealthy code execution technique. The main application is code injection, but we'll see there's another kind of flavor that can be useful in malware development. So yeah, we're going to go through a technical talk, but I hate commenting code, so I try to stick to just high-level principles and show as little snippets of code as possible. That's not the kind of talks I think people enjoy. So let's move on to the most exciting slide of the presentation, which is the legal one. So essentially that says that this is my own work, not my employer's. And a few words on me. So what's my background? So I'm Hugo. If you haven't identified this accent, I'm French. I also go by that handle that you may have seen on Discord, Twitter, RWX Stoned. And I work in a red team, so an internal red team. Adversary emulation, I believe is the term right now. And I've had, before that, some blue team background, and even before the blue team, more generic IT, sysadmin, DevOps style. So if I'm being honest, way less interesting than, obviously, hacking. And I've got a blog where I publish some stuff from time to time. So this is going to go into one article when I get around doing it, writing it. But essentially, with that presentation today, I'm going to release a GitHub repo, make it public. And yeah, as I said, it's going to be a POC kind of demo of templates of code with helpers function that kind of facilitate reproducing what the ideas I'm going to explain here. And then if you want to reuse those principles, those ideas, put them into your implants or your C2 or your techniques, then that's great. So this morning we had a talk on lateral movement and from Kevin Ott. And there was a bit of a retrospective, like where do we come from? What's the history? And I like these types of approach of going back, a few years and kind of seeing trends. And sometimes you see weird patterns like cycles, and you think something has died forever, and somehow it makes a comeback in a new flavor. It becomes a useful technique again. So just to put things back into perspective, let's go back to the beginning or beginnings. So depending on your age, you probably started with that. When you were magically teleporting your implant from process to the next one. I talked yesterday on the boat to people in their 20s, so maybe they didn't actually do that, but we've got all ages in the audience, so at least half of you here know what I'm talking about. And at the time, there was no real concern about process injection because there were no in-memory detection. So yeah, as I said, pretty much magic command, type it, it works, that's it, you're in a different process, and no questions asked, no real... I remember thinking that's really magical, that's wizardry to me, like this, how that worked. And then obviously the cat and mouse game between security vendors, red teamers started, and you had to innovate. So an illustration of that is Cobalt Strike, giving you, for instance, the ability to play a bit with how exactly you would inject code, use different APIs. So that gives you several levers to pull, to play with, to make your actions look a bit different. So you see complexities growing, basically. Now the field continues expanding. New techniques appear here and there. Great research. People go deeper and deeper. Here you have another illustration, a fairly recent write-up from our friend at Outflank, so early cascade injection. Just an illustration to show you as I said, the trends. So that's recent stuff. That's less than a year ago, I believe. Now, historically, generally speaking, and I'm saying generally because we'll see a few exceptions afterwards, there's been 3 ingredients when you perform injection. So at a high level, you needed to write memory somewhere, write something into memory. Depending on how you write it or where you write it, you usually have to somehow adjust memory. So that's the second action. And the third one was to trigger it or invoke it. Whichever way you do it, you need an active action at some point to make stuff happen. Here I've put this API, the most well-known. There are several flavors of that, but you get the idea, the philosophy here. So for us, red teamers, or I know it's red and blue. I don't really know the ratio. That would actually be interesting to know. We seem to have inferred, because you can never really be sure, that the last step is the dangerous one. So there is an EDR watching, there is a drone over you, basically, looking at telemetry events happening on an endpoint. And there's a build-up of events, and it looks like, in general, what gets payloads burnt, or maybe even your whole operation burnt, is that tricky final step, which is CreateRemoteThread. And the result, if your EDR works well, is this. So I'm not going to name named. We've heard some product names before that may not, probably not notice anything unusual with that types of payload. But at least, even if you don't get your payload burned, it's probably going to become very nervous and scrutinize what you're doing really up close. So memory scans and stuff like that. So I mentioned several techniques. There was an outlier that I didn't put in there. And I think that's the first, although I'm not an historian, I haven't gone to look back at all the timestamps and dates, but I think that was the first approach to this idea of injection, where you wouldn't perform that final step of triggering something. And here the idea, so threadless, I think the inspiration in how Kerry Coburn named that was that you don't create a thread, is that somehow it's going to happen naturally on its own. So you do the steps, you start with the steps that I mentioned previously. You write something in memory, but you write it carefully somewhere in memory that is going to be executed later on by something, somehow. So you leave the execution to something else, which in that case would be the intended natural flow of the process that would execute your payload, thinking it's the natural original code, but it's actually something you've put in there. Very carefully chosen place. So I would say that kind of demonstrates there are 2 categories. One that I would call the active injection technique, where you trigger it yourself through an API call, generally. And the second one being the passive one, where you hope that something will run it on your behalf at some point. So for us, red teamer, what's the benefits? Obviously, it's stealthier. It creates less noise on endpoints. But there is a price to pay, and that price is more development, more testing, because there is a higher stability risk. So we'll come to that, because it turns out that this aspect is where most of the work goes with those techniques, is making sure everything stays stable and doesn't go completely off the rail. If you want to go back to those slides to see all the actual injection techniques that there are, I was surprised that there's quite a lot. And there's a nice list there on that GitHub repo, so I've put it there as a reference. Apologies for the weird drinking sound. So a bit more formally, to summarize what we've said. Active versus passive injection technique. So active, you rely on well-known APIs that are now, we know they are really scrutinized by security products. So here you see the 3 really famous ones, the 3 pillars of all those classical injection techniques. If you're using a passive technique, you just really care about writing. So obviously that flies under the radar in a lot of cases. That comes with a higher stability risk, because you are completely derailing the normal execution flow of the program. you don't have to be too much concerned about that when you are using CreateRemoteThread, because its function is to create a thread and run stuff. And obviously, that means more development effort, more testing, more lab time, basically. So as I was writing those slides, I came across this article published by Checkpoint Research, so from Hasharazad. Don't know how to pronounce. I never know how to pronounce those names you see on the internet, and one day you have to say it out loud, and it sounds weird. So great research, which is kind of playing exactly on these ideas I was talking about, and hijacking a waiting thread. So that sticks to the philosophy I was just describing. So now what, with these general ideas and concepts put there, what's the one I'm bringing to the table? So as I said, I'm going to release, it's not going to be a tool, it's more examples, a POC, if you will, of how to run code that way. Now, there are two flavors, as I said, and just to avoid confusion. If you stick to one process, you can use that to run code execution within your process. So that's sometimes called API proxying, which is essentially you're a malware developer, you want to run something sensitive. So I'm going to say virtual alloc all the time. You want to run virtual alloc, it's best to not run it directly. We've seen, for instance, ColdStrike developing Beacon Gate, which kind of gives you tools to implement that type of stuff. We've seen other C2 doing API proxying for certain API calls. So the part of the GitHub repo that's dealing with that is going to be, and the slides referring to that are in blue, just to say we're in the same process. And it's more interesting and it's sexier when it's process injection and you're doing it in a remote process, in which case it's in red. I just want to remind you of those colors that I'm going to put later to be sure everyone is not getting lost between those two scenarios. So what are we going to do? We're going to write payload somewhere, fix memory, and then we're going to overwrite one address that we know Windows is going to use at some point. Windows is going to look at that address and trust it and execute something that's there. Now, when is Windows going to do that? Exactly, it's asynchronous. There's a bit of randomness. But it's going to execute it, hopefully. And in that case, it's going to, and we'll see how and why, it's going to execute it if a thread is created. So that's going to be the trigger. When a thread is created in the process is then going to pick up the payload with put it in somewhere in memory. So what do I mean by wait for it to run naturally, and what does that bring us, that type of stuff? So we know call stacks, or at least how something was invoked, is important, because we know security products start looking at it. In that case, it's ultimately triggered by a normal behavior of your process, whether it's the one you're at now, where your implant is running as, or the one you're trying to inject into, let's say Chrome or Firefox. And it puts decorrelation in your attack chain. So again, the talk this morning on lateral movement was saying, okay, if you wait 2 minutes, 3 minutes, sometimes that's enough to confuse an EDR. If you think of basic analysis, heuristic analysis, or even automatic checks, sandboxes, they might try to reproduce what you've done, but then because that last steps happens asynchronously, is triggered by something, maybe it won't happen, or it won't happen unless a user actively does something. So it maybe won't be reproduced in a sandbox. So at least it frustrates a bit the defensive controls that we are up against as red teamers. So again, yeah, just a reminder of how that's going to look like, these two flavors of the idea I'm talking about. In the project, there is loader shuffle. Again, I'm not great at finding names, which is the one where you play with those entry points in your process. And the one where you inject is loader inject. So two sub-projects with two kind of examples ready to compile and run, and that we'll see. There's an example of message box that I'm going to play in a demo a bit later. So API proxying in blue, again, and process injection in red. So I've alluded to modules, DLLs in Windows. So obviously, maybe a small refresher on what DLLs are is needed. But I'm not going to make a lecture. I hate those types of talks with a lot of theory. So I'm not going to go through that. And anyway, we're going to focus only on the bit of the DLL that we need, and it's really tiny. What we're interested in is if any of you has started running DLLs, compiling their own DLLs for testing something or for trying DLL sideloading payloads or that type of stuff. I think you're like me, you never remember that weird syntax with the DLL main and the switch statement cases and all that. So you go back to the skeleton provided by Microsoft and you start with that. And essentially that tells you, Windows tells you, okay, if you want to write a DLL, you need to use that skeleton, that template. And we put our stuff in process attached in general. I'm not even going to talk about exports here. We just need to focus on those 4 cases here. Basically, we just care about process attached. We just care about what happens when Windows loads a module. But there are 3 other cases. So obviously, there is a kind of symmetrical of process attached, which is when the process is destructed, 2 cases related to processes. And there are those 2 thread-related cases in between. So they are kind of optional, not always happens. In general, modules are perfectly happy to live their life without anything provisioned for cases where a thread is created, but it's optional, and we'll see when it runs, when it doesn't run. But the way Windows looks at every type of module is through those kind of 4 cases. And if one of those cases happens, then Windows is going to try to run that DLL main and run the associated case. So either it's creating a process or destructing it, or maybe it's a thread creation or destruction. So I have to put that structure here because it's difficult to just talk about IDs. At some point, we need screenshots of stuff and actual data structure. So if you've done malware development, you've looked at those structures when you've been doing unhooking, identifying exports or API addresses and all of that. You need to loop through that famous doubly linked list of modules that tells you where they are loaded in memory, what are the addresses and all of that. So what do we have here in that WinDebug snippet, which has been truncated, but you've got name, you've got the name again in a different way, you've got load times, load reason, you've got several memory addresses, so there's a DLL base, there's the entry point. I think you see what I'm getting at. The entry point is a major player here. So there is the entry point. There's plenty of other stuff. There is a link to the following list, this slightly confusing concept in doubly linked list. And referring to this threads-related event, there is that flag called don't call for threads, which means that DLL doesn't care whatever happens for thread creation. We don't need to run DLL main. But sometimes it's on, sometimes it's off. Obviously, in the case where we're trying to hijack execution and we're trying to piggyback on that happening, we want the DLL main to be executed when threads are created. So shout out to Batsec from MDSec. Because I've been reusing a lot of the code snippets and reverse engineering that's been on all the Windows DLL mechanisms. So that was implemented in the Dark Loader library. A lot of stuff wasn't documented, but he's documented it. So yeah, I wanted to put a reference here to the great work. Okay, so again, let's go back to those 2 and put the 2 next to each other. And just to really highlight the important bit, which is that this entry point that you see on the right is the DLL main. So that's the same stuff. That's how Windows knows that the DLL main is at that certain place in memory. So let's summarize what we said, because that's the key idea of that's the main slide basically. If there was one slide, it's that one. So we have an entry point which tells Windows where a certain important function is in memory. And it's going to execute it for 4 possible scenarios, 2 for sure. We've seen that threads are optional. Process creation, destruction are not really useful for our case. We want to run during the normal life cycle of the process. It's already kick-started, everything is in place. And we need one of those modules that's going to be running the thread event switch case that we've seen. So we need a don't call for threads equals 0, which always messes up my brain. Like don't call for threads 0, which means run for threads equals 1. You know, we want something to run when threads are created. So that's the idea of the technique that I want to release today. So how does that look like if we take an example? So our favorite guinea pig process, Notepad, so classic stuff, Notepad in memory, you see the image, various modules, and that doubly linked list in memory sitting there in the green area. And as I've said, it has pointers pointing to all of those DLL mains for each of those modules, you know, 10, 15, 20, 30 modules loaded in your process. And that's how Windows knows where they are all and keeps tracks, knows where everything is in memory. Now, a lot of us have been playing with those memory structures, but have you ever wondered where is that linked list exactly? You know, usually there is that process where you go through the PEB and then the PEB tells you where it is and all that, but where is it actually? So I don't want to ask and get an awkward silence and no one wants to raise their hand or whatever, so I'm going to say it's on the heap. What's the advantage of that? Obviously, it's already read-write. So it's easy to modify. You know, it's not like you need to go in a weird section, change memory permission, and obviously that makes more noise. That's a bit more suspicious. That is on the heap. So you've got all those key information, those key structures on the heap, ready to be overwritten, just waiting for you to do it. So let's continue with that scenario that I've described. So we're going to break that link here for one of the module, and we're going to redirect to something else. So that something else here is a runner. So it's a helper function. It's a fake DLL main from Windows point of view. You know, it thinks it's going to run DLL main, and instead is going to invoke that runner, which is a wrapper around whatever you want to run later on. It's going to be invoked with the same argument as DLL main would be invoked, and that's useful. That's actually useful for the runner to know exactly why it's being called and you know, in what context. And then that runner, as we'll see, is a kind of helper function that's provided in the POC and is going to take care of performing whatever you want it to perform. So I've put the blue frame around. You see that means let's look at weaponization, but let's stay in one process. We stick to the process before we kind of translate these ideas to writing to a remote process. So far we've seen that it's fairly easy. You just need to override one pointer to get Windows to execute your code. But that's actually the easy bit. Then that's where the real trouble begins and all the work and the development effort. So the first thing is you've tampered with something which is really important, so you're going to get a crash unless you revert it fairly soon enough. So first thing is you need to restore the entry point as soon as possible. Then we're in the scenario where we want to run an API call. We don't want to run just shell code, okay? If it's process injection, we just want to run shell code. That's more acceptable. But here, I'm talking about API proxying. So we want to run a sensitive API, let's say virtual alloc again. So you need to pass arguments to it, and you need to get the return value back. So that adds complexity, and you need to think of a mechanism to do that. So again, I'm going to provide those functions, those templates that I'm demonstrating. They kind of give a helper that abstracts that away, and you know, obviously you can see how it's doing it in the background, but then there are ready-to-use templates that are there to simplify that work. And finally, a big constraint is that we're running in the context of a DLL main. So all that we're talking about, it's Windows that has started, that has been running a DLL main, essentially. We'll see that comes with several limitations. I'm sure you've come across them, probably. if you've been playing with stuff like DLL sideloading and trying to pop, let's say, a message box or a calc and it works, and then you put an implant and it doesn't work anymore. And the reason is because DLL main puts constraints that somehow prevent, I'll mention it a bit later, there are constraints on what can run in the DLL main on it. So I'm going to loop through those 3 bullet points and see exactly how they are addressed. So the first one is we need to restore whatever we've changed. Again, stability. So how is that done in the POC that I'm going to demonstrate? There is that function that comes very early in the scenario, which is restore loader. So whatever we've changed, we know our runner function has been invoked with certain arguments, and based on that argument, it's going to go back, see what's changed, and revert it back. So that's one challenge addressed. Now we want to pass arguments to it. So we are diverting execution flow to a runner. So that runner is going to go back to a structure that's placed on the heap. And essentially what that function is doing, that data structure is doing, is it's collecting all the information needed to run an API call. So you don't have to really be bothered about passing arguments and all of that. You put them on the heap, you fill in that structure. So you see mostly it's about putting argument and return values. And the runner will know to look back at that structure on memory, and then it will know what to run. So how does it look like? If we run a message box, it runs like that. You fill it in. You say it's got 4 arguments. I want to run message box. You give the 4 arguments, and then it's ready to roll. So I'm going to show you a demo. I'm going to pause here. Yeah, okay. So yeah, we're staying in process, so ignore the COBOL strike on the right. So I'm running this here. And here you see it's changed. It's played with the entry point of a module. So you see there is a new entry point essentially. So it's backed it up, and now it's waiting for a new thread to happen. When that new thread happens, our new entry point is going to get executed. Because it's a simple process that just does that, I think I'll have to stay here 10 minutes for a new thread to happen. You know, that happens in the background sometimes. You know, there are some weird worker threads that spontaneously appear doing nothing. So to not make this awkward, I'm going to trigger a thread. You know, I'm going to simulate a thread being created by pressing a key, and then that's going to kickstart that stuff that I've talked about. So it's run the message box in that dummy thread that was created here. Yeah, that version, okay, it's taking a bit. So, yeah, and you see it goes back to normal background Windows, you know, APIs in NTDLL that are responsible for starting threads. And then it's collecting the return code, which is important. If you run stuff, you want to know if it has succeeded or not. And that's it. So we'll come back to that for the beacon later on. Right. So that's one demo. And there is a third bullet point here, which is that if we run in DLL main, there are limitations. And those limitations are actually quite hard to overcome. You can't really overcome them. You can only deal with them in a certain way. So that was message box. There is another example provided in the template, which is something more complex and something more interesting if you're running a C2, which is doing internet stuff. So whether it's WinINet, WinHTTP, if you want to do HTTP communications, you're going to have to use those more complex APIs like Internet Open, for instance. And that's not going to work in a DLL main because of deadlocks in thread syncing issues and stuff like that come from the fact that it runs in DLL main. So one way to work around that is to run it in a separate thread. So if you want to run your API call in a separate thread because it has that limitation, you can enable that flag in the data structure that I was mentioning before. So you switch it to 1, and then the runner will know that it has to run that in a separate thread, and it's going to run it, and you're going to get the result back, similarly to what I've been saying. For whatever relates to what you can do with DLL main or not, there's some official Microsoft documentation, so really useful. It says that you can't do much, basically. So yeah, it's good for, if you're running into issues related to DLLs, I would refer you to read that, because your problem is probably explained in that documentation. So now, can we translate that, all that we've been talking about? How does that apply to a remote process? So let's go back to our memory representation of a process. Not Notepad anymore. Let's look at Chrome, for instance. And similar ideas. We have that process. It's got its DLLs loaded and all of that. We want a payload somewhere in memory to be executed. So whatever we've been doing, we need to do it in a remote process, which is mostly writing stuff in that remote process. And again, we're going to identify a DLL in that remote process, and we're going to break that link here and have it execute our payload instead of running a usual DLL main for one of its DLL. And then we wait for that to happen. If it's Chrome, if it's more complicated processes, threads are being created all the time, so that's going to happen immediately. But you're free to add some complexity to that, and you could very easily, and you'll see after, you could really easily, for instance, make it only actually trigger after 10 or 15 thread creation. So it sits transparently and wait for a certain time, and only at some point you want it to detonate. Now, we've got a bit of challenges coming from what I've been describing. So again, that payload that runs, it needs to deal with these issues that I've been talking about, mainly around stability. So whatever you run needs to take care of that. It needs to have a kind of preamble or preliminary code, a code step at the beginning that's going to do those 2 steps here, which is 1, restore the entry point. Second, continue in a new thread. Otherwise, here you're running a beacon, you're not running a message box or just a virtual alloc, you're running a full-on beacon. You're going to end up with thread syncing issues and all of these types of problems, especially if you use HTTP libraries. How am I doing that? So then we're startly moving into implant development and all of that, and that's not really the point of the talk. You're free to implement that the way you want. If you've got your own C2, that's perfect. If you use CobbleStrike, one way to do so, they haven't paid me anything. I keep mentioning CobbleStrike a lot, but I find that that UDRL feature that they've added lately is very useful, because that lets you add some customization to what exactly happens when you run a raw beacon. And if you were to run a raw beacon, that wouldn't work, because those 2 steps here are not taken into account. So you need something that's compatible with that technique to revert the changes you've made into Chrome when you start injecting into it. So for that demo, I've used a pretty standard payload, CobbleStrike payload, pretty standard UDRL as well. Now UDRL is its own license, so it's not published with that. I'm showing snippets of code and the ideas, and then you're free to reproduce it the way you want. So what that's going to do is, first thing is restore the overwritten value. So that's generally that's the idea here. I'm not going to comment every line of code. It's boring, but essentially it's saying unless you're in the right scenario, do nothing, which is the first block. Just sit there transparently and run the normal DLL main. If it's the right scenario, then revert, and you see an entry point being restored and stuff being shuffled back into place as it was before everything was messed up. Second point, continue in a new thread. Again, very simple step for that demo. You just create a thread and continue running your loader, and then we're back to normal COBOL strike in that case, normal execution and normal reflective loading, and you end up with a beacon. So I've tested that on Windows 10, Windows 11. I've done a lot of testing because obviously it feels dangerous to do these types of manipulations into processes. So tested the browsers, I've tested the Explorer, a lot of different types of app, .NET or unmanaged. And that good results, good stability. However, I want to bring that back to the table with all of those techniques, all of those passive injections types of technique. There is a high stability risk because you may put all of the efforts you want into making sure things are put back into place as they should be. You're still tampering quite seriously with how the process was designed to work. So there is that risk. And basically, it boils down to do a lot of testing and try to test scenarios which are as close as possible to what you're going to encounter in your operations, in terms of versions and stuff like that. So let's hopefully get some beacons. Right, so first I'm going to inject into Notepad here a favorite one. So that beacon.bin here is the UDRL payload that I was just talking about. And so hopefully a thread won't happen as I'm talking. Usually it takes a while. So what we see here is it's looped through some DLLs, you see, and it says it's found the DLL number 9, and it's done some changes. It swapped the entry point and making sure now that it's pointing to your payload. Why DLL number 9 is because in the code, in the logic that goes through the DLLs to identify which one to change, I'm skipping the first ones. The first one are always anti-DLL kernel, key DLLs that out of safety concerns, I don't like to mess around with those. So it starts from later DLLs, like 5 or 6 or something like that. It's hard-coded. Obviously, you can change it if you want. So at that point, everything has been changed. It's just waiting for a thread to occur in Notepad. So sometimes that happens out of the blue. But usually, if you start interacting with it, doing stuff, like that, yeah, okay, so now it happens. So you see, you've got to somehow make it create a thread, interact with it. So that's not bad. So if it's Firefox, threads are created all the time. So that's going to happen much more quickly. So let's do the same. So same, it's injecting into Firefox. No beacon straight away, but now something just had to wait a few seconds. We can do it in Explorer as well, just to show you it works. And same, if I interact a bit and make it do something there, you get your beacon. So that was the, thank you. Yeah, big relief it worked. I had the videos ready in case, but okay. Yeah, so I'm going to leave you with that. And I'm going to publish it, I'm going to make it public just after in the next few minutes. I've created a link here. Sorry. So I'm going to leave you with that. That's the repo that I'm going to make public, and that's a QR code. Sorry, let me put it on the screen, 2 tabs. Yeah, so it's still private, but yeah, that's going to be loader shuffle as a few templates. So feel free to add your layer. I'm sure plenty of people are going to look at it and say that I did it a dumb way, and they're going to find smart ways to do things even better. And that's the logic of community. So thanks very much for your attention, and hope you enjoyed the talk. Thank you.